Everybody. Apologies for the early start, but I'll try and keep us on time this morning. So I think I'll just get started with the parish notices, and then if the last few people drift in, we can go from there and hopefully start at 1:30. There's a few things I've been asked to remind you of just before we get underway with the actual session this morning. First of all, the standard fire alarm stuff. If the fire alarm does go off, there's no planned test or anything like that, so please evacuate out the nearest exit. If you find yourself going out the back of the building behind me, then the muster point is next to the swimming pool. If you go out the front, then it's on the promenade, so basically just cross over the road and head on to the promenade. Photos are being taken throughout the event, as if you were here yesterday, you would have seen. Just to remind you that if you don't want to appear in photos that are then used on the website or any print media or anything afterwards, then if you get a red wristband from the SRP ladies at reception, they will make sure that you don't appear in photos. At the end of the conference, there will be a link sent out to you for feedback about everything to do with conference. So it would obviously greatly help SRP and the organisers if you could complete that and send it back, please. The exhibitors, I suspect most of you by now know where the exhibitors are. Please don't say hello. And also a reminder that there is both the affiliated organisation 5 minutes sort of talks during the breaks. I think the programme for that is sort of near the little area where they're doing those talks. So if there's any companies that particularly interest you, just go and have a look for them. And then also there's the on the app there's the rating or voting for the best exhibitor. So please remember to do that at some point today so it can be awarded. A reminder for Charlene that if you have not done so, please remember to book your seat for the annual dinner tonight on the app. Everybody, there's a sort of, if you go to social meals, there is a book table feature. If you don't do it in advance, you will be allocated with some random table or sat by yourself on an empty table. So suggest you do that. And finally, for the session we're about to go into, the Q&A, so though we will have a couple of roving mics around the hall, there's also the ability to enter questions on the app that will then appear on my iPad on the screen, and we can sort of ask speakers directly. So if you fancy doing that, that's probably quite a nice way of making sure that we get through sort of the best questions. If you could, because we've obviously got a number of speakers this morning, if you could put the name of the speaker that you'd like to ask the question to at the start of the question, that'd be really helpful, because otherwise we just don't have a whole load of questions, not quite knowing who to aim it at. Yes, I think that is everything. So, we'll get started with the first talk. So Leo is up first, Leo Blaauw. Leo is the radiation protection engineer at Sizewell B. Leo graduated from University of Warwick with a degree in physics. He went on to complete a PhD in magnetic Compton scattering at the same institution. Upon graduating, Leo's first job was as a health physicist at Chapel Cross. And 3 years later, Leo joined EDF as a radiological protection engineer at Sizewell B and gained his RPA certification 2 years later. Leo specialises in the maintenance and testing of Sizewell's radiological instrumentation, and his other interests include remote monitoring and helidosimetry systems and their application to the various challenges that arise on the station, particularly during the refuelling outages every 18 months. So Leo is over to you.
Thank you. So, morning everybody. So my colleagues from Chapel Cross have been introducing me as the instrument geek who lives in a cupboard at Sizewell. I have got a cupboard, I don't live in it though. It's full of instruments. So thermal sleeves, you might have seen it in the news because Sizewell was off for a considerable period last outage because of the issues. I wish I could say that on the day that happened, I went into the outage control center, which is like a command and control center for the outage. And I was confronted by a very concerned fuel route engineer. He said, Leo, we've got a problem with the thermal sleeves. And I said, what's one of them then? Do we need them? So for your benefit and for mine, what is a thermal sleeve? So this is a schematic of a standard PWR. Sizewell is an American-designed Westinghouse 4-loop PWR. And the thermal sleeves sit just at the top here, these funnel-shaped objects. And they provide a lead-in during reactive reassembly for the control rod drive shafts, and they protect the control rod drive mechanisms from thermal transients as those control rods are retracted and placed into the core, and if the reactor head spray is ever used. So to get a bit of context, during an outage, the head of a PWR needs to be removed and the bolting flanges across just above that green section there. And the idea is, what's supposed to happen is you take the head off, put it on a storage stand, and everything you see red above there is supposed to go with the reactor head. And then it goes and sits on a stand. And then the next stage is the green section there is what we call the upper internals. And that controls support, has support columns and other support plates for the drive mechanism, for the control rods. That also needs to be removed so we can finally access the fuel underneath for refueling. And then reactor assembly is the reverse process. So those funnels on the end of the guide tubes, the thermal sleeves, provide a lead-in for those vertical sections as they re-enter the core. So during construction, those thermal sleeves are put in from the top. So you can see here, up here, there are nuclear safety significant welds. So basically, that's the pressure boundary up here. So they're installed before those welds are finished, and they sit in the adapter tubes quite happily. And then they go underneath a nice clean head that's not been used yet, and they weld on the trumpet section. So schematics are one thing, but just to give you a sense of scale, that's a reactor pressure vessel head under construction. And those are the tubes I was telling you about that are welded afterwards once the thermal sleeves are installed. You don't really get a sense of scale. So on the right there is Sizewell's head on the stand. So you can see the bolting ring here is the same bolting ring. Once all of the gubbins, if you like, are installed in the head, it's a very large structure. And it's placed on a storage stand, which has an entrance door for inspections. But we don't routinely go under there for reasons that you'll see in a minute. Underneath the head, so that's a view. If you do crawl underneath the head and look up, you see the thermal sleeves, and you see the adapter tubes that the thermal sleeves sit in. This is what happened when we lifted the head last outage. It's very hard to see, I appreciate on that, but you can just about make out there the funnel-shaped thermal sleeve sitting on the upper internals after the head was removed. Immediately we saw that, we knew we had a big problem, because that's not supposed to be there. It's supposed to go with the head and stay on the head. So we knew straight away we had to at least recover that one. And we had to understand what had happened. Now, thermal sleeve detachment is a known phenomenon with PWRs. But for reasons I'll get into in a minute, we didn't expect it to happen yet. So what had actually happened? Well, the thermal sleeve sits in the adapter tube like that. And I don't know about you, when I first saw that, I thought, that's not a very good design, because the sharp edges of the thermal sleeve are resting on that ledge of the adapter tube. And what happens, because they're just sat there with a friction fit, essentially, they move as reactor coolant is circulating. The thermal sleeves will rattle around, and they will begin to wear themselves down. And as they wear, they drop through the adapter tube. And you can see there, if you keep going straight up, you end up with a detached thermal sleeve and a remnant ring remaining in the adapter tube at the top. So the challenge is, if that happens, the thermal sleeve will just pull out, but the remnant ring is still stuck at the top. So as I said, we knew this was a phenomenon that happened on PWRs, but there's an interesting, if you just Google it, there's an interesting American study by the NRC that looked at thermal sleeves and the wear rates, and they said that the mean time to failure for the first failure was over 50 years for a PWR, and the less than a 2% chance of a failure within 25 years. Now, Sizewell B's head was replaced in 2006 for other reasons, I think as a result of Davis-Bessey incidents, and it had less than 15 full power years because of the outages that last every 18 months, that last a few months. It hadn't had a long time basically in service. But there was some evidence from the French fleet, the PWR fleet, that the wear rates were slightly higher, but Sizewell was an American design. So to be cautious, we decided, ironically, that very outage that we were going to do laser scanning under the head of the thermal sleeves to determine how far they'd worn already. So you can imagine our surprise when we took the head off and one was already out. We were expecting to do a study and say, well, they've worn a bit, but it's only been 15 years. So when we did that scanning, which we were all set up to do anyway, we found another 15 that were unacceptably worn, either on the verge of failure, or there were actually 1 or 2 that had already failed, but that were held in by friction. So how do we fix this? Well, going back to my first question, in RP, we always like to ask, well, do we really need to do anything? Because it's not going to be very nice if we have to do anything. So my first question was, really, do we need to do anything? Can we operate without them? But nuclear safety being the overriding priority, the answer quickly came back, no, you can't. You need them. So then we had 2 options. The first was to dismantle the entire reactor head and to cut open the pressure boundary welds at the top and extract it from the top, extract any remnant rings and machine from the top. The other was to do underhead jumps. So that picture I showed you earlier where the head's on the stand, there's an access hatch for crawling in, and we'd have to do a repair that way. The early analysis of both those methods predicted about 140 millisieverts for collected dose either way. But the top-down approach needed very, very long time, months longer than the underneath and it required cutting these wells, which are nuclear safety significant and would have required a lot of NDT and etc. afterwards. And to give you a bit of context, every day that Sizewell is off in lost generation is over £1 million. So when the analysis was done, the cost-benefit analysis, etc., the cost for the underhead repair was about half of the top-down approach, and for the top-down approach, it would be over £100 million to repair. So underhead repair was preferred. So that's what we plan to do. So Westinghouse have a technique for doing this because it is a known phenomenon. They have done it in the States, and they've done it I think recently in South Korea. And that involved what we call electrical discharge machining. I'm not an expert on that, so don't ask me too many questions about electrical discharge machining. Again, Google it, because that's what I did. High discharge current basically can cut through the stainless steel of the thermal sleeve. And like I said, that remnant ring that could be remained would have to be broken up. Or if a sleeve hasn't failed already, we had to make 3 vertical cuts and 3 horizontal cuts to leave us with a detached thermal sleeve and some remnants that we could then remotely grab with some tools. Then those adapter tubes needed to be flushed and inspected, and then a new compressible thermal sleeve is installed. So a compressible thermal sleeves are essentially the trumpet end cut into sections and held closed by compression. I can't show you the actual mechanism that's used because it's proprietary technology, but basically it's inserted compressed, it gets up to the top of the housing, and then the compression is released and the petals spread out like a flower, and then it sits where the original thermal sleeve sat. So what was the hazard? Hopefully you can see some of those numbers. This was the sleeve that was removed from the upper internals from underwater, and then taken to a separate building on site, a tented area to inspect. I'm not going to discuss the tented area that we used for there, but tens of milli per hour at the end, because it's the end that sees the reactor coolant more. It's got a greater surface area. It's closer in terms of neutron flux to the core. And full-scale deflection on swabs that we had to measure in terms of dose rate because the instruments were going full scale. I say full scale, but just to give you context, 2,000 counts per second on the instruments that were being used was full scale. So you can imagine that any project that goes on for a long time, everybody starts to come up with names for things to help time go by a bit quicker. So these became known variously as crusty cornets, dodgy didgeridoos, and I think my personal favorite was honking horns. That we had to go and deal with. So again, we got 15 out in the end. So under the head, that's not me. The text would have to be over here a bit more, I think, if it was. One of my colleagues went under as an initial jump to determine the radiation gradient underneath the head, and it's quite significant. So at crouching level, it's 5 millisieverts per hour, but up at the directly underneath where the thermal sleeves are, it's 20 millisieverts per hour, give or take. So we had an idea, and then of course we were concerned with IDOS because, as most of us know, the limit changed recently, and because of that difference in gradient of say a meter or half a meter, there was this concern that we would exceed I-dose limits. So we had to obviously manage the whole body doses and their I-dose limits, and we also had to worry about airborne activity generated during aggressive tasks such as the cutting. As it turned out, the cutting uses uses water as a coolant fluid, so we had to control that. So it helped keep airborne activity down a bit because it was essentially a wet cutting technique. Then we had to worry about the handling and storage of thermal sleeves. So there's the old adage in DIY, you measure twice and you cut once. In something like this, once something's been removed, it gets measured 17,000 times. 20,000 photos are taken by every engineer that you come across, despite RP saying, do you really need to take more photos? The answer is always yes. It's nuclear safety significant. We must take a photo, which is understandable. But you did feel after many shifts, this is getting a bit excessive. Every sleeve that came out was examined and a significant amount of dose was accrued. So how do we control the dose? So Westinghouse, as soon as they were working up the tender for doing this process, they did practice runs. They had a lot of training on rigs at their facility in the States. RP couldn't go because of COVID, so we were stuck in the UK with teleconferences, video conferences, etc., to discuss techniques and what support they would need from us. So where Geeky Me comes in is when the use of remote monitoring. So we needed to have teledosimetry of those individuals under the head. We needed to be able to talk to them because we had cameras under the head, and cameras to look at behaviors, etc., are pretty useless if you can't tell the person they're doing something wrong. So you need to have comms and the cameras. So that proved really handy in the end. And you'll see a video in a minute of a jump underneath the head to install the sleeve. Whilst people were waiting outside the head, so a lot of this stuff, like the cuts were set up and then they could run automatically, and then they'd go in and rotate for the next cut. So there was a lot of waiting around, but waiting around near a dosy reactor head. So we had to think about some shadow shielding for those people waiting outside. So management of I-dose, as I said, was a concern. So initially we used I-dose TLDs in positions inside radiological RPE, sorry, respiratory protective equipment, that's one. And of course, initially, the first few jumps, we immediately took those for analysis because we didn't have a good handle. We had the dose rate measurements we'd done under the head with a handheld instruments, but we didn't have a good handle yet on how that would translate exactly to whole body doses and I doses. So we were studying the doses as they came in to try and determine a ratio that we could work with. So for later on, once we had established that ratio, we could give people I-dose meters and tell them to keep them for a long time, for a month, rather than having to do every jump and sending them off for analysis. And I remember the head of RP being very nervous, waiting for those results to come through because of the I-dose limits. So anyone who's worked on a reactor, whether it's operational or decommissioning, knows reactor tape. Or a tape that a site uses, which essentially holds up nearly the entire station. And whenever you're doing a task like this, the rolls of plastic come out. If, in terms of environmental concerns, this isn't best because we did try and decontaminate the plastic as much as possible before we disposed of it. But we had to come up with the design of a tent around the storage stand. So you can just see that the head is sitting on the storage stand there. And we had to put some shadow shielding on top of the structure. So we worked with the scaffolders to build a suitable tent. I use the word tent kind of loosely because it doesn't look great, but it worked very well. And then this is an access. This is the head stand, and this is the access into the head. And obviously everyone's sign blind, but we do try our best with signs to warn the hazard. That's under the head. That's where you enter the head. So because it was a very large tent, we needed to worry about extracts to try and keep. You see on the reactor head there's a gap between the head and the stand, which you can't do a lot about. You wouldn't put a reactor tape on the flange of the reactor head because of foreign material concerns. So we had to make sure that our inflows was sufficient, that we were drawing air in through the reactor head and not letting anything to escape. And we had to make sure there was suitable extracts placed in the undressing area and things like that. So where people were waiting, airborne levels were kept low enough that although they were wearing RP the entire time they were inside the tented area. So that's just a kind of a top-down view. This became, as I said, things got nicknames. This became Neil's tent because one of the a newer engineer actually, who used to be an RP technician, he designed most of the tent for us. So it's his fault there's a smiley face down there because I didn't do that. I was assuming everyone would get out clean and happy when they'd finished. They got out clean for the majority, but I'm not sure about happy after you've been in a power hood for several hours. So it gives you an idea of scale. That's the head. Cables for teledosimetry, etc., had to be run from remote locations. A bit of context with that is that Sizewell, although it's the newest operational station in the UK, it was designed in the 80s and constructed in the 90s. And in containment, there are 2 LAN ports in containment for every bit of data that needs to come out of containment. So that's a challenge because you can imagine having a house with 2 electrical sockets. 2 LAN points in the containment meant that we had trailing sockets upon trailing sockets of LAN to try and get data out, which does work, but it's a nightmare to set up. These are Bob's boxes. So my other colleague, Bob, went down to a local manufacturer, a metal fabricator, and had designed by himself a storage box and said, we need to take these thermal sleeves, we need to take them out of the building, and we need to store them for eventual disposal. So we had these boxes designed, and we did a lot of trial runs with dummy weights, etc., dummy pipes of stainless steel, so that by the time we came to handle these, we were very practiced at getting them out of the area quickly and getting them across to the building that they were going to be stored in. And that made sure that the risk of contamination spread was very low as well. So very quickly, it's just a 1-minute video of showing you a jump to install a sleeve under the head. So in this video, everything has been removed from the penetration. It's been cleaned, inspected, and it's ready for the installation. I wish they moved that fast in real life. It's about double speed, this. So later on, there was obviously that platform took a while to orientate, and that's a bit of the OPEX that we'll discuss later. But there's the thermal sleeve with the compression mechanism that I can't zoom in on. So then they're just rotating it to make sure it's fitted correctly inside the adapter tube. And that was it. So that's how quick we got to be with underhead jumps. But as you'll see later on, that jump would have given those 2 people of the order of a couple of 100 microsieverts for that one jump, and they would do multiple jumps. So this is the graph of the doses that we did for each sleeve. It is kind of in order. But the outlier here, this one F10, is the one that was recovered from the upper internals. So it didn't have a lot of cutting tasks, etc. But it had a lot more inspection dose. Surprise, surprise. So we did kind of get better, but there were issues along the way with stuck sleeves. Those pieces of remnant that stay up there sometimes would go play hideaway. So the cameras couldn't find them. So it took a while to make sure we had everything. But overall, the doses did come down, and we were quite pleased with our performance by the end. So that's a graph that every physicist would love to see. So that's the correlation between eye dose and whole body dose. So when we were plotting that, we couldn't really believe how accurately it came out as 2 to 1. The odd outlier here, we think there's 2 things that could have happened. Either that individual spent a lot of time sitting on a chair outside of the head and made all of his mates do the jumps, or he forgot to wear his eye dose meter. We never actually got to the bottom of which one it was, but that's what we believe is that outlier there. But everything else, more or less, there's a nice trend line. We could say 2 to 1. So we could start controlling eye dose by controlling whole body dose. And we did it that way, and it works extremely well. And it kind of correlated with the dose rates we were seeing under the head with a handheld instrument anyway. So that's a summary of the tasks. So they're separated into the inspection team and the installation team because the inspection team were a separate group of people. The thermal sleeve removal and installation tasks, you can see, based on the number of minutes they were on average spending, the dose rate was essentially about 100 microsieverts per minute that they were under the head. The mean for a jump was 180. I don't like having 181 because that's too precise for me, but very high doses, obviously. Overall, we were aiming for collective radiation exposure of 175 millisieverts. That was a bit more than the initial 140 because that was after we considered all of the inspections that were going to be required of the removed sleeves. We came in at 135. Maximum dose we were shooting for was 6, half the whole body, and 5.9. Maximum lens to the eye was 15, and we got 12.2. So number of PCEs, I don't know why we didn't just put 0 rather than not applicable. We don't have a goal. I think we should have had we don't want to get anyone contaminated goal, but we got 3 people ended up becoming contaminated. Now, this talk was written for an American audience, and the EPRI level 1, for those of you who aren't familiar, EPRI level 1 is roughly 100 counts by a pancake Geiger. Anything less than that is a level 1 PCE. So all 3 personal contamination events we had were EPRI level 1, and we believe every single one was due to undressing behaviors when they took the powered hoods off. They cross-contaminated their heads and things like that. But overall, given the number of jumps and the number of people, we were pretty pleased with that performance. So, lessons learned. What went really well was our relationship with Westinghouse and our combined working, because those guys said that it was the best RP they'd ever worked with, and they've worked around the world. So that was quite pleasing to hear. The use of remote monitoring. I didn't write this slide, so I'm not blowing my own trumpet there. And that worked really well. And Westinghouse had their own cameras that we need to assist with them because they bought American TVs that didn't work in the UK and things like this. We obviously, after the first sleeve was done, you saw the high dose for that one. A lot of learning went into that. I put a detailed post-job debrief to make sure we captured all of the learning. The remote monitoring you saw, and the fact that I can show you the video, is because that all went onto the network. And so their own lead team for Westinghouse could be watching their workers working in the UK whilst they could watch it on site, and they could export that data to their colleagues in the States and give feedback. And because of the comms, the way it was comms set up, they could actually, through a chain of people, talk directly to the workers in there without having to remove them from the work area. What could we have done better? Well, we would all like to go to the States. That would be nice. Not because it was a jolly, but because it would have been very important for us to work with them from the start. You saw when they did the underhead jump, the moving around of the platform and trying to get it in the right position. We could have done better with some kind of fixed work height platform. They kept having to adjust it depending on which task they were doing, the inspection, the machining, the installation. And likewise, the tool lengths, you saw them bring in the thermal sleeve tool and how high up they had to get to make sure it was in properly. We could have done something with modified tools to give us keep everyone lower on the head and keep their doses down. But overall, we're quite pleased. It was 2 months of work to do the installations, do the removal installations, and 2 months of planning before that. But I don't think we could have asked for it to go much better, to be honest. So that's actually it. So, any questions?